Okay, so it's time, and so we can start. Good evening, everybody. It's a pleasure to have you with us today. And 1 minute, it's also a pleasure to welcome David Jackson to give the 16th OSMU lecture of this year. David is an experimental particle physicist by training, and since 2006, he has been working as an independent researcher on theoretical ideas in unification. David was an undergrad in physics at Nottingham University and obtained his master's from Cambridge. His PhD in experimental particle physics was from Lancaster University, and during which he also worked at the LF experiment of LEP at CERN. Subsequently, David was a postdoc at Rutherford Appleton Laboratory at Stanford and also at the Keiki Laboratory in Japan. This was followed by a lecturer's position in particle physics at Oxford, and then in 2006, David shifted to becoming an independent researcher working on a theory of unification, which he has been developing over nearly the last 20 years at least. So this is what we'll hear from him about today under the title, Unification by Generalizing Proper Time Rather than Appending Dimensions of Space. So great. Over to you, David.
Hi, Jitendra. So thank you very much for the introduction, and thank you very much for organising this series of talks. Thanks everybody also for joining. Good afternoon, good morning, good evening, different people. So one of the things I like about this lecture series is the possibility to talk about different ideas. So before giving a brief outline, I'll just talk about what's different about this idea of generalising proper time. So if you think of general relativity, we start with four-dimensional space-time and a proper time interval, delta S, with a metric in coordinates in four-dimensional space-time, and then augment this to some higher dimensional space-time structure, represented here in more than 4 space-time dimensions, then compactify down the extra dimensions, leaving either one or several residual dimensions, and try to use this as a kind of source of matter. So this is the familiar approach of extraspatial dimensions. The alternative here is to start at the local level, essentially the local inertial reference frame, and generalize the local Lorentzian structure. So rather than having just a quadratic form, we're going to go up to a p-th order form where these alpha coefficients generalize the metric coefficients with zeros and ones. But as well as going to n greater than 4 components, we've also got more than 2 powers. So it could be a cubic or a quartic form and so on. So this will have a larger symmetry I've called G hat, which generalizes from the Lorentz group. But this symmetry will be broken because we have to pick out these 4 preferred components. This will break down the symmetry to the original Lorentz external symmetry and an internal gauge symmetry. So this is the symmetry of the physics. So as consistent with things like the Coleman-Mandela theorem, this is not the symmetry. The full symmetry is not the symmetry of the physics. And the residual components in here, there's no geometric interpretation. I've drawn them as a circle just to represent it's a larger set of components. These components will be the basis for matter as transforming under this broken symmetry. So in particle physics, we're interested in local particle interactions, local symmetry properties. So this is a very direct way of getting some kind of local properties of matter on this indirect approach of extraspatial dimensions. So it's an alternative way of identifying matter by generalizing a kind of a metric structure. And the aim of this talk is to show that this idea of generalizing proper time in many ways is conceptually better motivated than extraspatial dimensions, and it's also empirically better suited to the kind of issues for unification. So a kind of brief outline, I'll say more about this motivation as a basis for unification. I'll then say how it connects with the standard model with an intrinsic role for the octonions. So this is how it connects to the octonion standard model and unification for this OSMU series of talks. But most OSMU approaches start with the pure mathematics involving, say, the octonion algebra, and then seek a connection with the standard model. Here, I started out by this conceptual foundation for unification based on generalizing proper time, which turns out to incorporate the octonions in a manner that's suited for the standard model. So I'm mainly going to focus on the conceptual picture of how the theory works and just summarize how it connects with the standard model and the mathematical structures involved. The next part of the talk, I'll talk about how you can kind of put together a framework for combining gravity with quantum theory. I'll spend several minutes at the outset here motivating, essentially taking classical general relativity and trying to identify quantum theory in a limit rather than trying to quantize gravity. So it's kind of the opposite approach. I think that'll be more or less the end of the talk then, but I do have slides on the cosmological connections with dark matter, dark energy, and other big picture questions. But I think what I'll do when I get to this point, I'll basically say why the theory has a cosmological dark sector and then skip to the summary. But I'll save these slides as backup if there's any interest in that in the discussion. So in the first slide, I compared this approach of generalizing proper time with using extra spatial dimensions. In the next slide, I'll say how it fits with classical general relativity. So here again, in general relativity, essentially the curvature of the four-dimensional space-time described by a metric tensor. So we can think of this as taking the Lorentz symmetry of an internal, a local inertial frame and generalizing this metric structure on the global scale. So globally, we no longer have the Lorentz metric structure. That's one way of thinking of general relativity. Whereas by contrast with that here, we're generalizing this local structure to higher orders beyond quadratic order with this idea of generalizing proper time. So it's a kind of a complementary way of generalizing the metric, but invariance of proper time is still central. And then we're going to identify this four-dimensional space-time part with a Lorentz symmetry, which will be part of this largest symmetry. That will break the largest symmetry. And as I said, these residual matter components will be identified in here, and that they will project over to the local kind of structure of matter in space-time. So if you think of general relativity and the Einstein equation, with the Einstein tensor equated with the energy momentum tensor, there's a famous discussion from Einstein in the 1930s where he likens the left-hand side to one wing of a building made of marble and the other side being like another wing of a building made of wood, and found this very unsatisfactory. And the idea of unified field theory, UFT, was to try to incorporate the wood into an augmented general relativity. So this is kind of consistent with that approach. We're augmenting the local metric structure, whereas most unified field theories from 100 years ago were augmenting the metric structure. But then they were trying to unify the gravitational field with the electromagnetic field, so it made sense to use a function of space-time, whereas here we're coming in at the local level, which might be more suitable for things like local particle interactions. So there's a general progression here from a kind of pre-relativity idea of time being a one-dimensional flow. So in relativity, it goes to a quadratic form. That's because the geometric structure of space is described by quadratic algebraic structures. So space-time has this quadratic form, and then the idea is to get space-time and matter. We can drop this quadratic assumption and go to the general Pth order expressions up here. And this is the general progression. The point being that in extending from four-dimensional space-time to incorporate matter, we don't need more space. There's no evidence for any more spatial dimensions. So we can drop this quadratic assumption and generalize not just to more than 4 components, but also powers greater than 2. So this new perspective means that rather than extra dimensions of space, the basic unifying entity is basically time on the left-hand side of this expression. That is, we can take an infinitesimal interval of time and take this as being a kind of arithmetic substructure of time, which we can write out with incorporating the quadratic structure of space-time still as a factor in one of these terms and expanding this. This just means further components of this delta x, making this up to a Pth order polynomial component, and all the residual parts are over here, some further Pth order polynomial, and these extra bits will be the basis of matter. So we can still pull out a four-dimensional space-time part as a quadratic substructure from this thing, but now we've got this residual matter part. So space-time and matter both kind of come out of this local structure of generalized proper time.
Could I ask a quick question?
Yeah, of course.
The number of independent coordinates is still 4 when P is more than 2?
Yes. The number of space-time components is 4. Oh, but no, sorry. These delta x's, there are much greater than 4 of these. This is there are more than 4 components. Only 4 of them will be space-time. The extra components are just interpreted as matter components. Okay. So it could be any number of components.
Thank you.
Yeah. Yeah, it's not like a there is something called Finsler geometry where you write down things like this where there are only 4 components and you're kind of generalizing Riemannian geometry. It's not like that. And we still have Riemannian geometry here over the original 4 components and kind of Einstein tensor and things like that. It's just that all these other things are extra components over and above space-time interpreted as a matter. So I'm going to try to kind of summarize in one slide why this approach is suitable for the standard model, without being too technical on the mathematics, just make it plausible that this approach might be useful for the standard model. So we're generalizing proper time from this 4-dimensional local Lorentz structure, a 4-dimensional space-time. There's a well-known way of embedding this quadratic form into the determinant of a 2x2 matrix. This is a well-known structure, 2x2 complex emission matrices. Taking the determinant of this, it gives the same quadratic structure, and this gives the double cover of the Lorentz group SL2C. The convenient thing about writing this in a determinant form is that we can easily go from a quadratic structure to a cubic structure by embedding this into a 3x3 matrix, that is 3x3 Hermitian complex matrices. And the 2x2 part is still contained within this. And this now has a full SL3 symmetry, and that is special linear transformations with 3x3 complex matrices. And this can be written out in terms of the determinant of this 2x2 part, which is the original quadratic part, multiplied by this delta x8 in standard way, plus other various cross terms. So this is a simple example of what I had on the last slide, where this generalized form of proper time will contain the 4-dimensional space-time part as a factor, as it is here, and then some other residual part, and all the extra parts here will be the basis for matter. So all these parts out here are the basis for matter here, and this is the space-time part here. Another thing we can do, as well as going to higher matrices, and this is where the octonions come in, we can generalize this structure beyond the complex numbers to higher hypercomplex numbers through the quaternions to the octonions, and we can also define a cubic determinant form over 3x3 complex 3x3 octonionic matrices. This gives it an SL3O symmetry. Now this has 27 components because each octonion has 8 components, whereas each complex number only has 2. So we have 3 times 8 plus 3 others gives us 27 components. This is a well-known structure, and in fact is a real form of E6. Once we have this E6 symmetry of a cubic structure as an expression for proper time, this also embeds in a quartic structure, well-known quartic structure, on a 56 component object, which is known as the Freudenthal triple system. But it basically contains 2 copies of this space, giving this 54 components and 2 others. But the point being that this has an E7 symmetry, and this E7 symmetry can also be considered as a symmetry of this generalized proper time. So by using generalized proper time, we directly connect with exceptional Lie groups. And the reason why this might be interesting is because if we look at the grand unified theories dating back, I guess dating back 50 years now, for internal gauge symmetry, there's a unifying sequence of gauge groups, originally SU5 and SO10, but they also bed in E6 and E7 up to E8, the largest exceptional Lie group. And these are well known to have connections with the standard model, as is also the case for the octonions. So generalizing proper time naturally kind of taps into these exceptional Lie groups and octonionic structures, and we have a symmetry breaking mechanism because we're going to pull out the original Lorentz symmetry for the external space-time. So this is not the same as a grand unified theory, because here we're also including the Lorentz group in this larger symmetry. So rather than going into technical details, I'm basically just going to state the result. However, I should acknowledge the main references for this. So lots of references involving E6, E7, lots of work by people who have given talks in this lecture series. But possibly the main reference comes from the Oregon State group. I think I may have seen Tevian in the audience, and Korean. They've also given talks earlier in this series. But their work on constructing this real form of E6 on this space is kind of exactly the thing I was looking for, to be able to kind of apply it, the details of this structure. So this is one of their references from about 12 years ago, and the references therein. So it's their work from about 15 years ago. So this construction relies very heavily on using that, but also cross-checking it with things like Dynkin diagrams, analysis, and so on. Okay, but the results come out, if we look at this E7 symmetry of this quartic form of time, this gets broken down to the external and internal form by taking these original 56 components and pulling out 4 of them. So we have the Lorentz symmetry acting on the external space-time. We identify, just comes out in the mathematics, an internal SU3 cross U1 symmetry. And then we can look at how these 56 components transform under this broken symmetry. And we get something like this. So this vector component is the external 4-dimensional space-time part. This is how all the other parts come out. So we get things like Dirac spinors, we get SU3 singlets and triplets. I'm just writing down U1 kind of charge magnitudes here, 1, 2/3, and 1/3. But we can sort of recognize things that look like, say, an electron spinor, Dirac spinor, which is transforms trivially under SU3 and has unit charge. And relative to that, for example, we have, say, a D quark doublet as a triplet under SU3 and a 3rd charge. So if we're looking for matter components, we do identify elements of the standard model here. From the point of view of the internal symmetry, we also get things transforming like U quarks and a left-handed, say, neutrino, but these have the wrong Lorentz spinor structure here. So the point being that this is rich in standard model structures. We do get Lorentz spinor structures, SU3 singlets and triplets, electromagnetic charges. And what's not shown here is that if you kind of cover up the Lorentz group, because E7 is known to be a grand unified group, it is possible to kind of identify elements of electroweak theory by covering up the Lorentz group and finding an electroweak kind of symmetry group which breaks this U1 electromagnetism, and also points to these components being associated with the Higgs. There's a lot of details I'm not going into here. I just want to make the point that this disconnects a lot of standard model-like properties coming out directly. And these components are also associated with Higgs just because they're closely related to the symmetry breaking structure. So this is certainly incomplete, and there are discrepancies, but there are a lot of properties of the standard model that come out this way, certainly far more directly than with extra spatial dimensions and with little redundancy. There's no extra kind of mirror partners or supersymmetric partners or anything like that. The main properties that are needed are that the U quarks and new leptons need to be spinors rather than these vectors and scalars. We need a full electroweak theory, and we need 3 generations. So this points to looking for something like a larger kind of form for proper time and a larger power, a larger number of components. And since we haven't yet used E8, it suggests looking for E8 of quintic or higher, possibly octic order, probably on 248 components, with that being the smallest non-trivial representation of E8 and with an octonion construction. And I haven't found such a thing, but this is a kind of a prediction of the theory to look for something like an E8 structure that generalizes beyond these E6 and E7 forms for a proper time. So I see this as one piece of a kind of a jigsaw puzzle to look for these kind of homogeneous polynomials incorporating 4-dimensional space-time. Now, I think when I say E8, people probably and recoil a little bit because it's known that E8 doesn't quite work with the standard model if you embed the Lorentz group and the standard model gauge groups in there. Well, I should say that that's when you do it at the level of kind of the Dinkin diagram analysis or the kind of standard Lie group representation theory. But here we're taking the kind of attitude that symmetry in some sense is more fundamental than group structure. And in particular, octonions introduce a kind of a twist in that they are non-associative and they can give rise to kind of non-standard representations. So I think the fact it's non-trivial that this can work means that it's a kind of non-trivial kind of test of the theory or prediction of the theory. As I say, it's just one part of the puzzle. So everybody working on things like octonion and exceptional Lie group unification schemes, the relations between octonion triality and spinors, and E8 octic invariant, all these are kind of parts of the puzzle that kind of need to come together. But this way of looking at generalized proper time contributes to the fact that it's providing a conceptual basis in terms of relations between space, time, and matter. And it kind of pins down this kind of structure to look for in terms of a homogeneous polynomial form as a higher order kind of generalized form of proper time and a symmetry breaking kind of mechanism. So my kind of high watermark for working on this was written up a few years ago in this arXiv paper. Now, rather than spending the whole talk talking about the mathematical technicalities, which would probably end up being a bit kind of falls short of finding the full standard model in any case. I think the sticking point is not so much these kind of group structures and using octonions and E6 and E7 and E8. The sticking point is more the fact that I'm using time as the basic element. I think when I have interactions with people, that seems to be the point that causes the most concern. So let me just address this conceptual issue of starting with time as the basic kind of element of the theory. So basically, if this works well for the standard model, why isn't it already being used? And I think it is because it just sounds implausibly simple to base a theory just on sort of time as the basic element. So for example, if you start with the extraspatial dimensions, you start out by adding something over the four-dimensional spacetime. So it sounds plausible that you can use this additional structure. Whereas here we're starting with something less than four-dimensional spacetime. So it raises questions how this local symmetry breaking structure can be related to extended spacetime, and more generally, how a sort of physical world and properties of matter out there in spacetime can come from time alone. And in the early days when I was thinking of this, I think the sticking point is because we tend to think of time as just being a line in space. So we often draw a line as either a space or as a kind of world line in space-time. And this gives us an impression of time just being this infinitely thin, structureless kind of thread, if you like. But I would say that there's nothing actually in the world that corresponds to this kind of image of time. This is just our kind of convenient kind of representation of a kind of time parameter. But it's not really what time is in any way. I think we have to go back, forget about the pictures of time and just think of it as a real continuum. And this real continuum says nothing explicit about any relation to spatial extension. It doesn't imply we have a line in space. So forget about these pictures of time and just think of it as a real continuum. When we think of the real continuum, well, this has arithmetic properties, not just a plus and minus, but kind of multiplying things together as well. And if the real line has these properties and the continuum of time is expressed by the real numbers, and then time itself can be considered to have these intrinsic properties. So the mathematics on the next slide is trivial, but it's really the kind of conceptual idea I'm trying to get across. So let's take this point of using more of the structure of the real numbers in describing time. So we can express time as this kind of linear way of adding intervals together, which is the usual way we think of time, just adding things in series. And if we do that, then these intervals fit together to compose a real line. Now, I've deliberately done what I said we shouldn't do, which is to draw time as a line in space. Which is why I've drawn it as a thick line. Which the only information is along this kind of R direction here. But we can also take these other arithmetic properties and we can write an interval of time using this quadratic structure. So this is still a way of kind of decomposing a small interval of time. We can write it this way. And if we can decompose our element of time this way, with these four components, we can think of this geometric structure of space being identified within this arithmetic substructure of time. That is, that this kind of arithmetic expression for an interval of time, which if I put this minus sign here and add these together, has a geometric interpretation, where these are essentially, these delta x's are intervals of effectively kind of local coordinate parameters. So we can think of...
quick question, sorry.
Yeah,
what
of course.
do you call x0?
Sorry?
What is x0 in your...
At the moment, that I'm just writing. That's coming up in a second. But I'm just pointing out that this part here is a three-dimensional spatial part. So I'm forgetting about this part at the moment. I'm just describing it because of the way you add lengths together in three-dimensional space. This has this property. If we write an interval of time in this possible arithmetic way, so it's the arithmetic expression comes before the geometry. The geometry comes after. It's the interpretation of writing it out this way. But if I don't answer your question in the next minute, please come back.
Sure. Please go ahead.
Yeah, so what I was going to say was that the important thing is that an equal sign can carry a lot of weight in the equations of physics. And the important thing is that here we're very much reading, we're very much reading this equation from left to right. So we're reading this as an expression for the proper time interval. So the whole four-dimensional thing, the four components, because of this minus sign in here, as the interpretation as a kind of a four-dimensional space-time element with a light cone structure. So this is the x naught you're asking about. Because of this minus sign, it has a different kind of interpretation to the other three components. So we can interpret this thing now as providing a local light cone element coming out of this expression for time. So this might sound a bit of an odd way of going about reconstructing four-dimensional space-time. So let me just make a little analogy here. So if you think of an ideal umbrella as being a folded one-dimensional object in space, and it starts to rain and you deploy the umbrella, and the whole thing opens up in three-dimensional space. So all of this three-dimensional structure is packed away through the geometrical kind of construction of the umbrella into a one-dimensional line. Here we're trying to analogous thing for time, where we're taking a kind of one-dimensional component of time, but we're arithmetically embedding in this quadratic structure within this kind of element of time and opening up as a space-time interval. Now, it might seem odd to mix space and time, but that's kind of what relativity does. You mix your space and time components. So if we think of this element as being an expression of time, then whereas these intervals fit together in a kind of along the real line, because of this kind of quadratic structure and this interpretation as a light cone element, these elements kind of fit together rather in R4. So if we take several of these things, these will fit together to form an extended region of space-time, which we can then take to the continuum limit. So this will be no residual discrete structure, and this one will carry kind of causal relations with it. So we get the kind of a causal structure with a local light cone inertial reference frame at any location, essentially. So the idea is to use this arithmetic intrinsic substructure of the real line to kind of express time flowing in a space-time. So the arithmetic substructure of time contains a geometric form within which it propagates. That's the basic idea of the theory. Rather than thinking of the geometry in space existing first, then drawing a line of time in it, time can carry with it this substructure, which we can interpret as a kind of a space-time structure. And that can be taken to the extended kind of manifold structure like this, a larger manifold, the same construction. And then these lines of time that we draw in it, these are just time-like world lines which we might attach to objects in space-time, but these are only elements within the full temporal structure. The whole thing is a temporal structure, and that we just draw world lines when sort of galaxies or people propagate through the space-time as an approximation. So I guess what I have in mind here is work on, the overall geometry will have a general, more general metric tensor description of the geometry. But the overall description I'm thinking of is things like when people reconstruct space-time geometry from a causal structure, which goes back to theorems dating in the 1970s, people like Hawking, Malamont, that if you have a causal structure, that's enough to pin down a metric structure within a kind of a conformal or volume element kind of level. So the idea is that the causal structure, which is a big motivation, for example, of a causal set theory, goes a long way to giving you your space-time structure. Here we're getting the full space-time structure by opening out these elements of time. And you might ask, well, what's the advantage of thinking of it this way, thinking of these things as being elements of time expressed in space-time? And the advantage is that then once we're thinking of this an expression for time, there's nothing to stop us generalizing this, going to the generalized expression for proper time, from which we can embed our four-dimensional space-time part plus fill out this matter content from the first part of the talk. And as I showed in the first part of the talk, the mathematical rules that this implies lead to direct connections with the standard model of particle physics. So a bit like the umbrella analogy, I'll put in one more little analogy here. So if you take a flat sheet of paper, there's certain things you can do, folding it in certain ways, and within the kind of rules of origami, there are a certain finite number of things that you can make. But it takes a certain amount of skill to work out how to actually make something out of this. You can't make any shape out of a flat sheet of paper. Here we're kind of unfolding the structures of matter, essentially from an infinitesimal element of one component of time, one-dimensional object. So it's very restrictive in terms of what you can get out of this homogeneous polynomial. So it's quite interesting that if we take this route, it does actually channel things towards standard model kind of structures, which are quite esoteric. So it's quite a distinctive kind of signature. But now, because we're taking these elements here as composing a kind of an extended space-time, then these matter content will fill out a full kind of space-time structure. So these extra components exist everywhere in the space-time and fill out the matter content. But the way we've constructed this is that we have a four-dimensional space-time block. But it's essentially a space-time block, but it's built out of the flow of time. We're using elements of time to build this space-time block, which describes this dynamic evolution of matter. So just by way of an analogy, this block is a bit like a kind of a river, where the fixed part, the block part, is like the bed and the banks of the river. It looks like a static thing, but it contains everywhere a flow of water. Here we've built a space-time, but it contains everywhere a flow of time passing through this forward light cone structure everywhere. So if we think of general relativity, that's associated with a four-dimensional block picture. The Einstein field equation is solutions for a four-dimensional space-time geometry, whereas the dynamic picture is what we associate with quantum theory. So we've combined these two things. So this is possibly a kind of a useful kind of environment for thinking about how to combine general relativity and quantum mechanics. So the next part of the talk, I'll talk about how we might go about combining general relativity with quantum theory. Well, I'm going to start by making a few slides which are independent of this theory, and just make some comments about the problem of combining general relativity with quantum theory. And on this slide, on the left-hand side, I'm going to make what I think is a non-controversial observation about general relativity. On the right-hand side, I'm going to make what I think is actually a controversial observation about quantum theory. I might have this the wrong way around, but I think most people will agree with this, and many people might disagree with what I'm about to say about quantum theory. So the non-controversial observation is that general relativity is compatible with indeterminacy. All I mean by this is if we take a heavy weight, which is kind of two halves glued together but uniform density hanging from a thread. So this is the picture of a kind of bowling ball on a rubber sheet. So this is in general relativity, the matter is associated with the curvature of space-time, and it's going to be slowly rotating. But we fitted this two halves of these two hemispheres with a small explosive device, and at some point we detonate this thing and it flies apart, and that changes this space-time geometry. So all of this is completely consistent with general relativity, because in the Einstein field equation, everything doesn't necessarily follow a geodesic. You have to take into account the laws of energy momentum matter on the right-hand side, including things like electromagnetism and explosive devices, which can deviate things from a geodesic. This kind of setup is completely consistent with general relativity. However, I said this thing was slowly rotating, so we could set this thing off at any time, and we could choose this time randomly. We could even set the timing of this thing, say with the timing of a radioactive decay or something. So this can be completely indeterministic. So the progression of events in space-time can have indeterministic features as long as they're consistent with things like energy momentum conservation and be consistent with general relativity. So this might sound controversial because of Einstein's famous aversion to the idea of God playing dice, but I mean, general relativity itself is a deterministic theory, but energy momentum can have indeterministic characteristics. And this is relevant because in quantum theory, and this is one of the experiments that Tejinder mentioned I used to work on in the 1990s based in the US. So in particle physics experiments, when you have particles flying out, so this is an event at the Z0, where you've got producing two quarks which hadronize into showers of jets, but the angle theta, or phi here, that these come out is completely indeterministic. So these indeterministic elements of quantum theory are not themselves inconsistent with general relativity. So now let me make my controversial comment about quantum theory, and that is to question whether quantum mechanics is compatible with probability. All I mean by this is that normally what we mean by probability is a relative frequency. So if you roll dice, you count the number of ways a certain outcome can happen over the total number of possibilities, and you divide one by the other, and that gives you your relative frequency. However, that's never what happens in quantum mechanics. That's never the way things are calculated. Instead, probability is a complex amplitude squared, which models probability. So a unitary evolution of your initial state, you still conserve probability when you sum over all possible final states. So you can model probability this way, but it's not actually describing what a probability is. So yeah, the controversial comment is that yes, this works pragmatically, but there's something possibly quite provisional about this way of calculating probabilities. And the point is that general relativity is not compatible with the way that quantum mechanics calculates probabilities because of the kind of evolution of wave function and wave function collapse and those discontinuities. So GR is happy with indeterminacy, but not with quantum mechanics. So when we try to combine quantum mechanics with general relativity, something somewhere has to give. And normally it's on the side of general relativity. So most approaches to quantum gravity attempt to quantize gravity or the space-time geometry or something like that. But let me just try this kind of logical sequence of arguments here. The general relativity is incompatible with quantum theory, but not with quantum phenomena. The general relativity is not ruled out by any empirical observation or collection of observations. I think this is a true kind of statement. There's no theorem to demonstrate that quantum theory can't be reformulated in a manner consistent with classical general relativity and with all empirical quantum phenomena. It's a bit like, because of Bell's theorem, if Bell's inequalities weren't violated in all experiments, then quantum theory would be wrong. There's been no similar theorem to kind of rule out general relativity. So that would be kind of a significant result, and I don't think that's ever been done. So as far as we can tell, all observations that we've ever seen in a laboratory are perfectly consistent with general relativity, and it could be that quantum theory needs reformulating to fit it with general relativity. So yes, I think there's a logical possibility, or more than a logical possibility, that the quantizing gravity is the wrong approach, and classical GR may prevail over a reformulated basis for quantum physics. And there's kind of a precedent for this, because when quantum mechanics was combined with special relativity to make quantum field theory, special relativity, things like Lorentz causality, Lorentz symmetry and causality, all these properties were fully retained, and it was quantum theory that had to be adapted to fit with special relativity. So relativity kind of prevailed over quantum mechanics. So I'm asking whether the same thing could be true of general relativity. The reason why I think quantum theory is generally given the upper hand is because while they're both unfailingly empirically tested and verified, quantum theory has been more extensively tested because it's easier to test in the laboratory. So this raises the question, if quantum theory is conceptually wrong, how can it be so successful? So let me try to address this point. So I just need to, let me just try to address this point. So the typical example is the electron dipole moment, which in quantum electrodynamics can be the anomalous magnetic moment, can be calculated very precisely in QED to about 10 significant figures or so. And it's well known that when you actually measure this experimentally, you get agreement out to 10 significant figures. So if these results are very successful, how could the means of calculation be wrong? And I think a clue to this, well, first of all, let me say that we're dealing with the most elementary known systems with the fewest moving parts. This is just a single electron, for example. So our intuition of accuracy is not necessarily that reliable. Another significant point is that I think that often in quantum theory, bootstrap techniques have been used, dating from the 1960s, but also from modern day in QCD. And these bootstrap techniques that demonstrate that reasonable constraints actually go quite a long way. So things like probability conservation by unitarity, locality causality, and symmetries such as Lorentz invariance can do an awful lot about what can and can't happen in these processes. And the only thing that really quantum field theory adds is specific fields and interactions of a Lagrangian and then perturbative calculation. And these could just be considered a more exhaustive set of constraints, basically. But I think there's a possibility that despite the great pragmatic success, quantum field theory, to coin a phrase, could be playing all the right notes, but not necessarily in the right order. It has all the right constraints. It's just forcing something out, but it's not necessarily the right way of doing it. So it's not, I think there is a logical possibility that quantum field theory and quantum mechanics could be reformulated. So as well as the successes of quantum theory, there are also many, many issues. So one is the fact that we have to combine general relativity with it somehow. There's my own thing suggesting that using amplitudes is not really what probabilities are. Probability is really relative frequency, but there are people concerned about, for example, infinities that occur in these calculations. So there's a bit of an issue with amplitudes. And I haven't even yet mentioned the measurement problem. So in the measurement problem, this is normally considered to be an interface between quantum and classical systems. So you've got these two different things that have to come together. Well, there's another issue here, that there's a time difference between when a particle is emitted in the double slit experiment and when something is detected. And there was a question about where does the energy go? So I mean, how quantum mechanics says nothing about what happens to the energy in a double slit experiment. Because there's a question of energy momentum conservation. And while quantum theory is very successful in things like the anomalous magnetic moment of the electron, it also has a few failures, like the quantum vacuum energy is far too high, possibly the worst prediction in science sometimes. So it's not always correct. And then why quantum theory? Where does it come from? Where do these kind of assumptions of quantum theory come from? So there are many, many issues for quantum theory, and possibly really only one issue for general relativity, which is the first one here. So this is just trying to kind of maybe address these things and think of these as clues for mutual resolution. So, for example, the complex amplitudes are really central to all these problems, all these three problems, in that it is the way of calculating amplitudes for abilities which gets the inconsistency with general relativity, and it's also central to the kind of the measurement problem. So I'll try to argue that this approach of generalized proper time possibly provides a way forward for this kind of amalgamation of gravity with quantum theory, and in particular by giving general relativity the upper hand over quantum theory. So for the last part of the talk, I'll do a quick survey of how this might work. There are three reasons, first of all, why generalized proper time might be well suited to this question. One is that what I mentioned earlier, that we're building up from the local level. So we're finding these local elements of space-time from within our element of generalized proper time, and then constructing space-time with its matter content. So it's not that we're starting with space-time, then quantizing fields and matter and so on. And we're actually looking at the composition of space-time from the beginning. And the related point, I said that the problem of time in quantum gravity, the different way that time is treated in quantum theory and gravity, is essentially turned inside out, because here the whole theory is constructed around time. And again, on a related point, the action principle in quantum field theory is actually closely linked with the idea of time. So in the history, say Newtonian gravity, you take some action by integrating a certain function over time, and that gives you these Newtonian orbits. In general relativity, your action is basically proper time itself already, as expressed in the curved space-time. And when you extremize this action for different paths, you get this kind of geodesic trajectory in the advance of the perihelion of Mercury, that sort of thing. So there is a kind of a history of the relation between time and the action principle. Even 100 years ago, Kaluza found that when he took his five-dimensional space-time geodesic equation with certain assumptions about its extra dimension, he could recover the motion of a charged body in the gravitational field and the electromagnetic field. There's this idea of using this kind of progression in time, or this geodesic trajectory, or this kind of generalization of proper time to get access to these kind of non-gravitational forces. So here, whereas in relativity, we've only got this proper time interval, here we're generalizing proper time. So the idea is that in the symmetry breaking projection of this object, to get all the constraints out to replace the action of the standard model in the standard model Lagrangian. So this is where this part that will replace the kind of Lagrangian essentially. Okay, so if I go to these three questions, unifying gravity with quantum phenomena, how we can reproduce these amplitude calculations and the measurement problem, it's useful to think of a particular kind of a system where all these three things come together. So I'll go back, find a place where they come together from my background in particle physics. And this is where the 2-mile-long Stanford Linear Accelerator Center was when I was a postdoc over there. That event picture I showed earlier, so this collides electrons and positrons, it accelerates electrons and positrons and then collides them together at the energy of the Z0, about 90 GeV. And this was the event I showed earlier. These detectors are about, well, this detector about 10 meters high. This is the same event. We zoom in by another factor of 100, then the inner part of this thing is a pixel detector, these very precise tracking the information. So we can extrapolate tracks in and zoom in by another factor of 10. And we see that not all of these charge tracks come from the central interaction point, but there's displaced vertices here. And these events could be identified as an E plus E minus going to a Z0 going to B quarks, because these B quarks form then part of B hadrons, which can travel about 2 or 3 millimeters at their boosted energy, and their lifetime is about a picosecond or so. And we worked a lot on these events from a particle physics standard model point of view when we're analyzing this data, but they're also very interesting here because all of this stuff is quantum activity. It's kind of hanging in the vacuum. There's no detector elements here. The nearest detector element is about an order of magnitude further away. So I think these events are really interesting from all of these questions because there's energy momentum going into this event, producing the Z0 and coming out again. So we can ask, where does the energy momentum actually go? Is it related by Einstein field equation to general relativity? What's this four-dimensional space-time curvature? So it relates very much to how we can unify gravity with quantum theory. It involves thoroughly indeterministic quantum processes where we employ amplitudes throughout. I think one thing that's a little bit underappreciated about these events is the measurement problem, because as I said, the nearest detector elements are way out here somewhere. So in the double slit experiment, you basically record one hit and you're done with the measurement. Here you record thousands of pieces of information. It might be a year later until you fully calibrate your detector and actually reconstruct these things. So figuring out what's going on inside these events, I think, are very interesting from this kind of quantum gravity point of view. And I think I'm just mentioning this because I'm really coming at it from how quantum theory and gravity can come together in these kind of systems rather than just at the Planck scale. And you might say, well, we can't do experiments. We can't measure gravity here. Well, we can't measure anything at the Planck scale. At least we can measure something here. So if we have a theory of combining gravity with quantum theory in this kind of environment, then at least we might be able to make some deviations or predictions if we're reformulating quantum theory. So so let me just go through very quickly how gravity might be unified with quantum theory in these phenomena. Now, as I say, we can't see the gravitational field in these events, but the picture that comes to the picture that kind of develops when we think about this in the context of generalized proper time is that if you had some superpower and you were able to see the gravitational field, very, very tiny gravitational fields, then what you would see in events like this is something like this. You would actually see, integrating over time, a kind of tiny curvature in the space-time geometry. So there would actually be a kind of space-time geometry with a metric and an Einstein tensor as a function of the metric constructed here. And here we're building space-time at the local level out of elements of matter fields from generalized proper time, as well as gauge fields from the symmetry breaking. So all these matter components are arising from the symmetry breaking components of generalized proper time over the four-dimensional space-time. And then we're defining energy momentum to be equal to this thing, basically. So general relativity, the Einstein equation, just comes in because we're building space-time geometry, and we're going to just identify the structure with energy momentum. And again, we're reading this expression here from left to right now. So usually this Einstein equation is read the other way, and the idea that matter somehow curves space-time. Here we're building space-time out of these components, and this will be identified with matter. So we're reading it from left to right. And quantum theory, we're coming from the properties of these field quantities here. So gravity is not quantized. There's no difficulty in quantizing gravity and no gravitons. Particles, elementary particles or particles of matter, smallest particles of matter are kind of propagating wave packets in matter and the gravitational fields. You can't normally think of waves in it because of the nonlinear field equation. You can't normally think of gravity this way, but because the gravity is so weak, you can use linearized general relativity, and you can write down wave equations and wave packets and so on. So these can be thought of as wave packets in the gravitational field as well as matter fields. And where there's an interaction, that comes in a kind of degeneracy of the description in these local matter fields. So whereas classical probability is the number of ways something can happen in space-time, quantum probability is the number of ways it is possible to build space-time itself. There's an intrinsic degeneracy in building the local structure of space-time, and that's what will give rise to this indeterminacy and quantum probabilities. So there is a difference in nature between classical and probabilities, but they both are kind of a number of ways frequency kind of thing, but one to do with the way we build space-time itself. So how might this conceivably be related to amplitudes? Well, I'm going to make this a very short story if I can. So the idea, if you're calculating a degeneracy, you could exchange the positive and negative frequency modes of these kind of wave packet contributions. So if we imagine now we've got our initial state wave packets going in and final state wave packets going out, this is our external geometry, the metric geometry. This is an internal degeneracy, and we're counting the number of ways we can exchange these different modes. So it's just a kind of a mathematical degeneracy. It's a very naturalistic idea of what a probability is, and that these are different ways of redescribing the kind of local geometry in terms of a different composition that give the same kind of geometric structure. And the constraint terms are going to come rather than from a Lagrangian. They're going to come from this breaking of generalized proper time. This expression here, this replaces a Lagrangian, so that these terms will arise from the breaking of generalized proper time, which will carry with it certain constraints on how fields can interact. And the way we interpret these kind of interaction terms, if we excite kind of wave-like structures, say in the matter components here, these phi components here, then we can leave this expression invariant just by sliding over these kind of exponential terms here. It's the same term, but we're moving the kind of particle excitation from say, the matter field here to the gauge field here. So this kind of sliding over replaces what you would normally do. So this comes in at this borderline here where we interchange between, say, matter fields and gauge fields. And this kind of sliding over of exponential components replaces the kind of mechanical role of creation annihilation operators in quantum field theory, which would occur in, say, interaction Hamiltonian terms, where these terms would be associated with, say a Feynman diagram vertex like this. And we can take this parallel between this construction and quantum theory further than this, and it's possible to find a formal similarity between how you expand these terms of degeneracy count, and I'm skipping a few steps here, as contributions to the imaginary part of the forward scattering amplitude, which via unitarity and the optical theorem is related to a total cross-section. So this is a total cross-section, and we need to unfold how to pick up particular final states here. But the point is, what I was saying about bootstrap theories is that basically there's very simple systems, and in this case we've got all the complete information from both sides. So at an elementary level, it's plausible that it can give the same kind of result. But we're kind of converting our amplitude calculation into a kind of degeneracy probability calculation. And the idea is to try to reconstruct all of quantum theory this way eventually. So I mentioned reading this equation from left to right. So we're basically taking the Bianchi identity to imply energy momentum conservation. That's why the Einstein tensor is so useful in this construction. So this implies energy momentum conservation. And actually this energy momentum or form momentum P so far is an independent object to these kind of wave 4 vectors. But these wave 4 vectors, they're also conserved in all of these exchanges. So they're independently conserved. And if you look at the actual velocity of a particle with this momentum, you get this fraction here. Similarly, a wave packet has a group velocity, which has a similar expression in the wave 3 vector and the frequency mode. So the idea is to use these constraints to get a universal relation between form momentum and form vector between interactions, and to kind of reproduce this kind of basic quantum relation between momentum and form vector without having to presuppose it. Okay, so to the measurement problem, basically we're using gravity as kind of one four-dimensional kind of solution to this thing. The fact that we can't detect this gravitational field, we basically use a wave function pragmatically to kind of give our best knowledge of what might happen. So there's no physical wave function collapse or measurement problem. And it's best to look at this in terms of the double slit experiment. So this represents our wave function as our best knowledge, but again, within the context of this new idea, if you had this superpower of being able to see the gravitational field, what you might see in these kind of events is a propagating wave packet in the gravitational field. But so again, looking at solutions for the Einstein equation with this inherent degeneracy. But now all of these processes are kind of enveloped in a four-dimensional space-time geometry. And here the propagating wave packet actually splits two ways. And it can split two ways because here the interaction occurs here and here. So this relation, this quantum relation only holds between the interactions. And actually through each slit, you can have the full wave vector, but only half the momentum passes there because this relation doesn't have to hold. And you might say, well, where does the charge go? This is an electron. Well, having a charge means the potential for interaction. We're not actually seeing that at the slits. So if you put a detector at one of these slits, then what would happen is that now between the interactions would have to have this relation again, and all the momentum would have to go one way. So we'd only see the particle going through one of the slits. So the idea here is to use the fact that in general relativity, the boundary conditions, including the potential for interactions now, are determining what can happen. And this kind of reflects the idea in quantum theory that a measurement depends on the apparatus setup. If you change the apparatus setup, you're basically changing the boundary conditions towards finding this space-time geometry. This is not an interpretation of quantum theory or any other interpretation. In principle, there are many solutions for this thing, but it's not many worlds. And it's not, of course, pilot wave, but there are actually sort of propagating wave packets going through this thing. So it has elements of these interpretations, but it's not an interpretation, it's more a reformulation of quantum theory. It still remains to explain how you can get the full kind of interference pattern. It makes sense that when these things are in phase, you get a peak, and out of phase, you get a trough. It's only to reproduce the full calculation. So all matter and all indeterministic events enveloped within a single four-dimensional space-time geometry. There are elements of retrocausality in this. And that's because you might say, well, when these wave packets emerge, how do they know that they have to kind of go in the same direction to kind of converge at this point? Well, these aren't really wave packets in, say, just the electromagnetic field going through a flat space-time. This is actually the shape of the space-time geometry itself. But using the fact that in general relativity, you have a four-dimensional full block solution that you have to find, which is being imposed on the structure of matter. So again, even if you have a delayed choice experiment, it's still part of the boundary conditions for the geometry. So the idea is overall to give general relativity the upper hand here and try to figure out what's really going on with quantum phenomena in terms of reproducing these amplitude calculations and avoiding things like the measurement problem. And the idea that these can come out as limiting approximations because of they work very well because of these constraints on these most elementary kind of levels of matter. And because we're changing what's happening in quantum theory, in principle, this kind of idea can be testable in the kind of boundary between quantum theory and classical kind of apparatus. So let me sort of head towards summing up. Again, this is just the main paper on this topic of quantum gravity. By quantum gravity, I mean combining quantum theory of gravity from the composition of space-time. But let me just get back to this idea of relations between space-time and matter. So almost all science is done this way in a framework of Newtonian physics or relativity, where you start up with space and time or four-dimensional space, and then you introduce kind of matter. The idea of extraspatial dimensions is that you get matter from extra parts of space. So if you take the local level, you're augmenting the right-hand side of this thing to a higher dimensional space in more than 4 space-time components, then using the extra components as the basis for matter. Here, by generalizing proper time, we're trying to get matter and space from time. So it's taking this same local element, but now we're generalizing essentially the left-hand side. We're generalizing the whole expression. We have something in general more complicated. That is, we have more than 4 components, but also powers p greater than 2. In practice, vector-spatial dimensions, we go to the global level, and then we have to compactify down. This is normally thought of being as a bad form of non-uniqueness, in that there are many ways of doing this. Here, because we're building up the structure from the local level, there's a kind of vast degeneracy built into the local level, but that underlies in this theory the kind of indeterminacy of quantum mechanics. So it's a good form of non-uniqueness. It's because this non-uniqueness is precisely the non-uniqueness of experiments in quantum theory. On the side of extraspatial dimensions, these are more familiar, and it may sound more plausible because we're adding something. And it's hard to see where you get from the model or quantum gravity or the dark sector. On this side, I would say it's arguably simpler and more unique and more constraining. It's more conservative because we're starting with time, which is something we're familiar with. And if you develop it, you can get out structures from the model and a framework for quantum gravity. And as I very briefly mentioned, it also provides a basis for a dark sector. And there's a clue in this picture here. So let me just strip out this picture and take it up to the top. So as I mentioned, when we go to these higher powers for proper time, there's this quartic form with an E7 symmetry based on the octonions, and these symmetry breaking structures led to structures resembling the standard model. Now, on the side of extraspatial dimensions, we could have done a similar thing, where we have this high dimensional form of space-time with this larger symmetry, and we could have broken the symmetry in just the same way by pulling out a Lorentz group. And this would give us matter fields that look like a kind of a scalar terms that transform as an M vector under SOM. So this looks nothing like the standard model. That's why this generalizing proper time works better for the standard model. On the other hand, we can interpret this as a possible way of generalizing proper time, just not with powers p greater than 2. It's still a possible augmentation of the local proper time interval. So because this matter transforms under SOM, it's completely independent of the standard model sector. So this would be kind of dark to what we see in the visible sector. So this provides a kind of hidden form of QCD as a kind of a candidate for dark matter from this parallel sector. And in fact, a candidate for self-interacting dark matter. Tejenda, do I have 5 minutes just to put some summary slides up?
Yeah, sure.
Okay, sorry, I meant to be finishing now, but I'm heading straight to summary slides now.
Perfect, no problem.
Let me just it'll probably take about 5 minutes to I just wanted to put up some references. Let me come in. Should be here. Yeah. So I haven't. So this is just some. If anybody's interested in references, basically, if you go into a literature search and put in generalized proper time, you'll get into papers on this. This is the most recent arXiv paper. And just say that there's a table in there that talks about all the problems of the standard model and quantum theory and cosmology. And these are kind of self-references to where these things are discussed in the context of this new theory. So all 14 earlier papers are cited in this paper, apart from the one on the octonions specifically, which is this other paper here. So yeah, this just to kind of everything is written up in great detail in all of these papers. I think it's over 1,000 pages or something altogether. But let me just finishing to sum up. So extraspatial dimensions are motivated in part by a progression in relations between space-time and matter towards a more unifying framework. So in Newtonian physics, you have space, absolute space and time independent, and then you introduce matter. In special relativity, on the global scale, you introduce proper time, and you have this Minkowski space-time. So it's more unifying because space and time are brought together. In general relativity, this quadratic form with Lorentz metric only applies locally. And what I mean by interlinking space-time and matter is that the Einstein field equation directly relates our space-time geometry with matter. So now we've kind of got one sort of interlinking thing. This partly motivates, I think, unified field theories and extraspatial dimensions, where you kind of augment the right-hand side of this to more than 4 components, and space-time is now your one basic thing, and matter somehow a subcomponent of your space-time. So what we're saying in the new theory is that this is one possible augmentation for our local proper time, our local space-time structure. But there's a further generalization, which put this thing to powers p greater than 2, and that transfers our interest to the left-hand side. So time becomes our basic unifying entity, and we're pulling out a quadratic form of space and the residual part of matter. So this can be seen as a kind of a further natural step along this kind of unifying trajectory. It involves stepping back to re-examine motivation, re-examine the basic motivation. So from special relativity to general relativity, the global flatness assumption was dropped. In here, going from extraspatial dimension to generalized proper time, we're dropping this quadratic assumption. We need a quadratic assumption for the spatial part, but not for the matter part. So the basis in time compared to extraspatial dimensions is arguably simpler, because we're just starting with time. It's more unique because time is just this one component. It's more unifying because we're getting space and matter out of time. It's more conservative because we're very familiar with time. We're not familiar with extra dimensions of space. And it's more direct because we're looking at the very, very direct symmetry breaking structures of this with no other assumptions. And it arguably represents the simplest possible unifying relation between space, time, and matter. So in putting everything from time, I think the main obstacle is that people might say it's obvious that you can't construct a theory that accounts for a complex physical world from time alone. It's just too simple. On the other side of this obstacle is it's kind of obvious that time does provide a unifying basis for the physical theory, since everything happens in time. Everything we observe, all experiments happen in time, and that the theory finds a way of actually describing that inside a kind of a theory. So it's a kind of a shift in worldview. Something that's quoted very often by many physicists is this quote, paraphrasing from Einstein, 1933, that everything should be made as simple as possible, but not simpler. And I quote it because I think this idea of simplicity is something that appeals to most people working in unification. So the trick here is to see how it's possible to construct a theory based just from time. So let me if I can briefly paraphrase this argument. It's best not to think of time as being a one-dimensional line in space or space-time. We'll just go back to time as being a continuum and think of these arithmetic properties of the real line as can apply to time itself. And that means that we can express time in a quadratic form. And we can locally derive the local structure of four-dimensional space-time from time by reading it this way from left to right. That then naturally generalizes to this general form for proper time. We can still pick out these quadratic forms as a basis for four-dimensional space-time, now with a matter content to fill up the full four-dimensional space-time. So it's a kind of change in perspective from time, something in the world, which is very enigmatic when you try to point to what time is. And the reason why time is enigmatic is that within this theory, the world is rather something in time. Time is the big sort of enveloping, unifying thing. And when you take this change in perspective, this seems to work very well for things like standard model, quantum gravity, and dark sector. So final slide. It's often also said that if you have a unifying theory, you want everything to come from one simple equation. And here, basically, everything does come from this one simple equation, which contains our basis for, say, space-time and matter. So again, we don't experience anything extra spatial dimensions, but everything we see, we do experience in time. So we're just using the continuum of time, which has this arithmetic substructure. We're not adding something of time, we're just recognizing the substructure within an element of time to construct space-time, and then this tends to work kind of better than extra spatial dimensions. It also provides a conceptual basis for introducing the octonions into physics, and that comes in because these cubic and quartic forms involve the octonions with E6 and E7 symmetry. I'll just flash through what I showed earlier about how this kind of reproduces elements of the standard model and the prediction for E8 to get a kind of full picture on the global structure. As I used to use these local degeneracies in constructing the four-dimensional space-time to amalgamate general relativity with quantum phenomena as a basis for quantum gravity. I'm also trying to reproduce amplitudes in terms of degeneracies for constructing the space-time, and also account for the measurement problem by taking into account this holistic kind of property of gravity. So these things are kind of all guides to kind of putting this theory together. And one thing that pins it together is replacing the action principle by invariance of generalized proper time, essentially giving these extra constraints, replacing the Lagrangian. So I showed this experiment from SLD, and the idea is that yes, here in these processes, we actually do have an enveloping geometry, and we kind of have the Einstein equation here fully used, if you like, relating the geometry with the energy momentum, and quantum theory comes in from this underlying degeneracy, and to try to connect this degeneracy with this formal similarity with components of the kind of amplitude calculation, and where the allowed kind of exchanges come from this kind of constraint terms. So these are all basically holding equations for what's really going on underneath, and these things really have to work together. And I didn't say much about dark structure, but I did mention this origami case that there are different ways that you can fold a sheet of paper and get out different objects. Here we're generalizing proper time over four-dimensional space-time. I've talked about this E7 branch to connect with the standard model, but there are other things you can do, including this quadratic structure. There's also another one involving matrix structures. So there are these other forms, and the idea is that these things have independent gauge sectors, so they automatically give you a dark sector in the theory. So I said a little about how this quadratic space-time form gives you an internal SOM. This other form here actually gives you a non-compact symmetry. And it turns out that there are things called phantom dark energy models, which use negative energy states. and a non-compact gauge group has negative energy states. And if you do a parallel analysis, this turns out to be a pretty good dark energy candidate. And this also contains a compact subgroup. This space-time form can also be augmented to include time-like extra dimensions. And if you did that, then this would also contain a non-compact gauge symmetry I've put out here. So both of these sectors basically contain compact subgroups within non-compact groups, which can be interpreted as a sort of a hidden QCD dark matter sector within this kind of phantom vacuum dark energy, and this kind of unifying picture of dark sector within kind of generalized proper time. And this kind of phantom vacuum energy, because it involves the creation of plus and minus gauge bosons, plus and minus energy gauge bosons out of the vacuum. In the early universe, in principle, that could be a testable source of kind of structure formation, which I haven't talked about. And then there are other things like big questions about what happened before the Big Bang and so on. So the overall picture is that in terms of conceptual basis, connecting with such standard model, framework for amalgamating gravity with quantum theory, cosmology dark sector, and the big picture, this approach of generalized proper time tends to give a pretty good kind of overall picture. This is not kind of an all or nothing picture. It would be possible to use this as a structure of matter, say for the standard model and the dark sector, and then just apply quantum field theory in the normal way. So it doesn't have to be an all or nothing, but it does seem to kind of work quite well for all of these areas. And of course, there are opportunities here for developing the theory. In principle, looking for this kind of largest form involving an E8 symmetry, exactly how this invariance of generalized proper time replaces the action principle, and exploring these other branches here. So there's plenty of opportunity for further work in this this idea. Anyway, yeah, sorry for going over, and thanks to Jinder, thanks everyone for listening. Thank you.
Great. Thank you, David, for a very interesting lecture and for your insights. I personally, of course, have a lot of things to discuss, so I'm sure others do. So let's take a 5-minute break. So we decided we'd take a break and come back in 5 minutes, and then we'll have your question.
Great, okay.
See you shortly.
Yeah, okay, thanks very much, thanks. Yeah.
Okay, we are back. Bernd, are you there?
Yes.
Yeah, go ahead, please.
I'm back. Okay. Actually, I have several questions, but for the convenience of the discussion, I will just start with the last question, which is on my mind. And this is related to your last slide, because you say you have phantom energy in your model. Is this correct?
That's right. Oh, well, I have negative energy states. That's right.
Okay. Normally, this causes quite a few alarm bells to ring.
Right.
Because normally you have then stability issues with your vacuum.
Yeah, so I think I will go back into some of these backup slides.
Okay.
Yeah, so the idea is, let me just see where I jumped out. Okay, this might be a good place to jump in. Am I still? Is my screen still sharing? Okay.
Yeah.
Yeah.
Yes.
Perfect.
Yeah. Okay, so the idea is, let me just get to this point. Okay, so we have this E7 symmetry here. As I mentioned, there are these other possible ways. So what I mentioned was that we can go to, say, 3x3, 4x4 matrix. This is still a kind of consistent form of this form of generalized proper time. And the thing is that when we look at the symmetry breaking here, we're going to get this kind of non-compact internal symmetry group. Okay, so let me just, and this is independent from us under model gauge groups. When I pull this thing out here, so let's see. Right, so yeah, so this is what you're saying, right? This non-compact gauge group has positive and negative kinetic energy states, right? Right. So the idea is that in phantom dark energy, that's can be worrying, because there you have these negative energy scalars, and they can interact with positive energy under model states through graviton exchange. Okay, and the equivalent thing here, because it's a non-abelian gauge theory, you can create these things out of the vacuum. Plus these subscript pluses and minuses, these are plus or minus energy. So this is quite catastrophic in some sense in the dark sector. But as I said, in this theory, gravity is not quantized, so there's no graviton exchange. And in principle, there are no particle exchanges between this dark sector and the visible sector. So this can be purely a classical gravitational link with this sector. That's the basic argument as to why it's possible to live with these negative kinetic
Okay, but even a classical theory with a negative kinetic energy is unstable.
Yeah, so well, the idea, okay, this is the idea. I mean, it comes from I don't have any slides on the phantom scalar models, but by doing a kind of parallel analysis, the idea is, let me just talk about the idea maybe, and then see if it's not a problem. So the idea is that because these things are being created out of the vacuum, they're going to fill the vacuum with these positive and negative kind of energy gauge bosons. And because every time you create a negative energy, it's going to be in a sea of positive energy, and vice versa. These things will also, to some extent, cancel out. So the idea is to fill the kind of vacuum state with this kind of plus or minus energy states. This can be completely gravitationally benign because basically you've got contributions to positive energy and positive pressure, but completely cancelled out by negative pressure and a negative energy. So this can give us a completely benign gravitational effect. But then we have to take into account that there are other matter states in this kind of dark sector, and these have a different equation of state that you would expect for the gauge fields. So these kind of asymmetrically perturb the equation of state. So you can get a small, in principle, no calculation here, but in principle you can get a positive energy density and a negative pressure as a vacuum solution, and that can give you a kind of a cosmological effect. That's the basic idea. And in fact, if you look at this dark energy candidate, so macroscopically, it's uniform in space and time because it's being created out of the vacuum. Equation of state -1, it doesn't change with time. Because this is what the vacuum looks like with these other positive energy states in there. So we do have a negative pressure, which we need for dark energy. You also have a cancellation, large part cancellation between positive and negative energy states. So you can get a very low energy density. The energy scale not necessarily as bad as the quantum field theory vacuum, because so for example, the quark-gluon plasma is about 10 to 44 times too large, but it still needs lots of large kind of cancellation. So yeah, but yeah, I think this is your point here. So it's analogous to models with phantom dark energy, but here, because we've only got a classical GR link within the model, it's in principle stable from a point of view of kind of elementary particle interactions. And it's also dark because of that reason. It also comes from a fundamental state. This kind of has the general properties that you would look for in a kind of a dark energy sector. Although this is a more speculative end of the theory, but yeah, I mean, it is possible to identify something like a dark energy model through these negative energy states, I think.
Okay, good. Thank you very much. Okay, then I'm done with my first question. So somebody else can ask.
So I lost my Zoom. I have to. I got it now. Yes.
Okay. More questions, please. Could I ask you something, David? Can we go to one of your early slides where you wrote a cubic proper time and related it to a 3x3 matrix? I wanted to understand something there. It was quite early on.
Let me see. So it's probably.
Yeah, this one. Yes, yeah.
Sure.
Is it possible to make it full screen?
Yeah.
Yes. So I wanted to understand a few related things. Firstly, did you say E7 is 4th power, delta S to the 4?
Yes, that comes. Yeah.
So this can be proved, is it?
Oh, I think it's just a well-known structure. I'm sorry, I didn't give any explicit references on this, but I think that this, well, I mean, obviously E6 and E7 as
E6 I can see.
Yeah.
So the exceptional Jordan algebra complexified, and your delta S cube as that is apparent. So I want to, E7 is a 4x4 matrix.
Sorry, it's not a matrix, no. Let me just try. Now this might be a bit dangerous to go into my backup slides, but I'll have a go.
It's okay. You can, if you can maybe send me some.
Yeah, well, I think it is a useful. Well, yeah, because I mean the point is that this E7 is not a
Because for octonions, I think we cannot have bigger than 3 by 3 matrices, right?
Oh no, that's right. Yeah, no, it's not a 3 by 3 matrix. It's going to be a bit.
It's not a 4 by 4 matrix, yeah.
So I'm hoping this slide will answer the question. Oh yeah, this was about. Oh yes, so basically, yeah, going to E7. It's often written as a matrix like this, but it's not actually a matrix. So it contains two objects, these H3O Jordan algebras, and two roots. So these are two copies of the.
So it's like combining two E6 kind of thing, is it?
Yes.
Okay.
And the quartic norm is
Okay.
written like, so it contains the determinant, and I forget the technical jargon for what these kind of these things are, these kind of functions, or these
Freudenthal product or something, yes.
Yeah, that's it. Yeah. I mean, it's all to do with the point of triple system and how these things are related.
Because the X and Y are elements of they are Jordan matrices.
That's right.
So yeah, and
No,
okay. Where can I read about this?
Oh, well, the best way I can think of is to
Tavian's book, is it?
I think Tevian does have one paper on. Well, there's one paper from E7 from about 10 years ago, I think. I don't know if he's still in the audience.
Corinne might still be here. I don't see Tavian.
Right, but the other thing is I think I'm sure that my own
Okay, I can contact you separately for this.
I mean this paper here, oops. This paper here contains a lot of E7 references.
Okay. Definitely. This is very interesting. So can we go back to that slide, please? I have a few more things to understand there. No, not here. In the talk. The cubic form.
Right. So you mean the complex level.
The slide that we were discussing.
Yeah.
The cubic form. Yes. Okay. And did you say that E8 would be delta S to the 8?
Oh, yeah. Okay. So where did I put that? Let me see.
I mean, I would have been happier with something like 5, you see.
Exactly. Well, if you I was originally thinking 5 because the E6 form is cubic.
Right.
The E7 is quartic. And in fact, if you look at my notation here, the E7, this is a small q for a quartic form. And I originally wrote my notation, I used q, thinking of this as being quintic. But so I was originally thinking quintic form, and it may still be. I mean, I don't know what this thing is, but there is something called an E8 optic invariant, which is based, I think, on Casimir operators and things. That was the reason for thinking it might be up to 8th order. So
I thought 8 might be too much, is because I see that you have, when you have n and p, your n is equals p square, I think. At least for when
no, that's only for yeah, that it is for the case of when this thing is the determinant of a kind of complex emission matrices, that then the number of components is equal to p squared. But in general, no, they're not related in that way.
Okay, so let's go back to that slide, please. So we can think over what's E8. Somehow I'll tell you why I would be happier with 5, because okay, so you have one interpretation for delta S cube as containing space-time from 0, 1, 2, 3, and the rest, presumably according to you, are matter coordinates, right?
Matter components, yeah, basis for matter components, yes, that's right.
So, many of us have tried to justify that H3O is the right place to describe 3 fermion generations. There's a different picture. And the way I would have brought in space-time is through a E8, which is like, in your language, that would be delta S phi, which is delta S cube into delta S, into a cubic form into a quadratic form. The nice thing about that is the cubic form would describe 3 fermion generations, and the quadratic form presumably could be used for space-time. So maybe what you are doing is perhaps the right thing, but I might have done it differently. Use delta S cube for 3 fermion generations into a delta S square for the space-time 4D line element, and together perhaps they form E8. I mean, that's just a guess.
Yeah, no, I think yeah, how to go about constructing this E8. I mean, that sounds like a possible approach. I mean, I think for part of the problem I have with this myself is that I do this kind of jigsaw, but I think it's just a kind of the wrong sort of metaphor, really. It's not like in a jigsaw you might put in one piece and another piece. I mean, I think the way I think of these is that these are more like kind of
We have a comment here.
oh,
Sorry to the Tavian here. The quartic invariant is described in one of Freudenthal's papers and is related to a generalization of the Freudenthal product on Jordan algebras. That was the 2 by 2 matrix you showed, David,
yeah.
right? The optic invariant is a mess, Tavian says, but is worked out in a paper by Sederwal and somebody in JMP. Yeah,
That's it,
I
yeah,
would like
2007,
to,
I
if
think.
I can, I would like to copy paste these. Okay, if you guys, if somebody else wants, you can please copy this important comment that Tavian made. I'll just copy it and keep it somewhere so that I don't lose it. I don't know whether the recordings preserve the
Right.
chat. I don't know. Okay, thanks, Tavian. Thanks so much. Thanks so much for that. So yeah, so just to read again, the quartic invariant is there in a paper by Freudenthal. That is so something to do with E7 and is related. Yes, the octic invariant is a mess. Okay, okay. I don't know about the octic invariant, but Tavian has given a reference. Thanks, Tavian. Go ahead, David, please.
Yeah, I think the quartic invariant on the E7 dates back Freudenthal around 1964 or something like that.
There's something like a phase space structure there, what you call the Freudenthal triple system, because in George Sparling's talk 2 talks ago, yeah, I remember that E7 is associated with a Freudenthal phase space. Is that what you also have in
I'm not
mind?
thinking of it as a phase space. I'm thinking of all these things in the same way, basically, as I said for the 3 by 3 case, the cubic.
Okay.
They all have the same interpretation.
Okay. I found your cubic form extremely interesting. I had not realized that the 3 by 3 matrix, basically, when you make the determinant, you can think of it. So when you pull, even that cubic form, if you pull out a quadratic, you will be left with a linear form. What does that mean then?
I didn't quite follow that.
Let's go back to that slide.
Okay, so
Yeah, so you mentioned that when you have a delta S to the P, you can pull out a quadratic form and you'll be left with something which is order P minus 2.
oh, that was yeah.
Yeah, so we can stay here. So if
Maybe
you
that was,
have a
yeah, this
cubic
one.
form here,
Yeah.
and
So it's
right, yeah. So here you pull out a quadratic, let P be 3. You let P be 3 and you pull out a quadratic form.
that's
You
right.
will be left with something linear.
Well, I mean, yeah, in the case of a cubic form, there's only one component here, this delta x8.
Yeah.
Obviously, for a quartic or quintic form, this would be a higher order.
Yeah. So, but in a cubic form, you are trying to separate space-time and matter components. So, what part is matter?
Basically everything that isn't the space-time part.
Yeah, so I'm
So
just trying to understand that matter.
maybe actually, I think maybe since you're asking about this, maybe it's useful if I'm not sure how well. Let's see. I think maybe it's just useful to go through this SL3 C case. I'm not see how these slides go. So yeah. So yeah, the idea is this cubic form. So these parts will be the matter here. I think the next slide shows it better. So when we pick out the external symmetry, that's going to act on this external part here. So that gives us our external 4 vector. And but this SL2C symmetry also acts on these components as a Weyl spinner, and well, this thing is a scalar. And then when we pick out our internal U1 symmetry in this case, this U1 symmetry will make this spinner into a kind of a charge spinner, whereas this one is neutral. So if we think of our overall structure, we've got these 9 components. We're picking out 4, and these 9 components decompose into the 4 of external space-time. These additional components here are all basis for matter. So part of it is a charge Weyl spinner, and part of it is just a scalar component. So this delta x stated as a scalar, whereas this part is a 2-component complex spinner.
Mhm.
And then this kind of generalizes to those higher order, like I said for
Yeah,
E7.
I get some idea. I'll go and read your papers and try to. I find this translation of cubic matrices into cubic proper times very interesting, and in
Yeah,
some
I think
sense
I've
it's
not seen anything.
unifying.
I've not seen anything else in the interest in the literature that goes beyond the quadratic form.
Yeah, right. Thank you.
But
Thank you.
I don't see any technical kind of objection to going
No,
to
I
cubic
think it
forms.
looks very interesting. Yeah. Bernd, you want to continue?
Yes. I try to better understand how you mix quantum theory with gravity. Do you gravitize quantum theory, or do you have something like emergent gravity together with quantum theory? This is not quite clear to me, at least not at the moment. So please.
I think gravity is kind of, or the Einstein field equation is kind of assumed on top of everything. So I don't think of gravity as being emergent. Basically, all that in combining gravity with quantum theory, all the give is on the quantum side in this picture, which I think is a kind of, as I try to explain, I think there's a logical loophole in the way there's no proof that Einstein equation doesn't hold to all scales, as far as we know. There's no evidence for that. If you ever have any counter examples.
Well, it predicts singularities.
Well, I kind of, yeah, I did gloss over that slightly, but I kind of what I was thinking. So when I put up this slide, let me come back up. I'm getting a bit, sorry. It's coming. This slide. Yeah, when I put up this slide about the problems with quantum theory, and I said that, well, gravity only has one problem, and that's how we combine it with quantum theory. I'm kind of including singularities in this kind of point here, because people who work on quantum gravity, one of the motivations is to understand the nature of a singularity. When my understanding of the singularity, when you get infinite curvature, you're also tending towards infinite mass density, and that kind of implies a need to understand what matter does in that environment. So you need a kind of theory combining quantum theory of gravity to understand singularities. That's why I'm kind of lumping that in this first problem here.
Okay.
Yeah, could I intervene if you don't mind? And
Sure.
no, David, there is a viewpoint that flat galaxy rotation curves are indicator of breakdown of general relativity. And I think of late this is becoming more serious because we had a couple of talks on wide binaries, and these wide binary stars people are saying from Gaia data indicate breakdown of GR, and there we cannot have dark matter because the scales are too small. And even more recently, JWST is detecting very early galaxy formation, and that is not good for lambda CDM. So
Not only very early galaxies, but also quite evolved galaxies already. So.
Oh yeah, sorry, I meant evolved in an early stage. That's
Yes,
what,
yes, that's the perfect way to describe it. They look
too
like
evolved
over
too
ages, so
early.
to speak.
Too evolved too early, not just galaxy formation. You are right, I agree. I meant evolution at very high red shifts.
Yes.
And
Well, it's both. So they develop faster than expected, and they are more massive than expected, but they're also, how to describe, more evolved. So also when you
yeah,
look at,
so they just saw last month there's a paper by Stacy McGough saying how this is much easier to understand with Milgrom's Mond than with the lambda CDM. So I think, in my view, there are these indicators, at least from my point of view, that at very large scales, GR might be getting dominated by a fifth force, which we can call Mond or something like that.
Yeah, I think these are still very open questions. I'm kind of using lambda CDM as a kind of standard guide, if you like.
Mhm.
But yeah, I think one of the difficulties with, for example, with dark energy, partly it's there is still some debate over empirically whether we really are observing accelerating expansion. But I think the difficulty of having a good theory of what dark energy is also part of the problem. So
Yeah, I would distinguish dark energy from dark matter.
oh, definitely, yeah.
Dark energy is an even harder problem, but already on galactic scales or in gravitational in wide binaries, uh, already I think there's a question that at low acceleration, basically at very low accelerations below the critical Mond acceleration, uh, we don't know. I mean, whether GR is holding, because since your question came up about GR at different domains or different scales. So
Yeah, well, one thing I tried to mention here was that I think I talked about I've got the picture here or not. Yeah, the fact that there are multiple different sectors of generalized proper time. So, and all these extra sectors, and I haven't even categorized how many there might be. They're all independent of visible matter. So there can be several different dark sectors. So there could be some with, say, different properties of dark matter, and some where the dark matter interacts with dark energy. So in principle, there are quite a few other parameters that can come here, or degrees of freedom, if
it
you
could be
like.
dark matter, or your generalized proper time could admit new forces. You see, that's also
Yeah,
possible.
no, yeah, that's a good point, actually. Yeah, so so I think
The fermion sector might even be intact as three fermion generations, and you might get more gauge fields. That also is possible, right?
yeah, I'm not sure if I mentioned it on here, but yeah, oh yeah, so right. So I think in terms of, it's a theory predictor. I don't really have predictions apart from predicting this E8 structure, but like the new physics is in the neutrino and Higgs sector, or combined Higgs neutrino sector. It's also possible that there could be new gauge symmetries coming in or
Yes,
new states. So
absolutely.
yeah, I think that this requires this full kind of E8 structure and to
Yes.
do the symmetry break and to make a comparison. So it's a bit
And
difficult to
also,
do that.
we have not seen anything beyond three fermion generations. And if three generations are described by H3O, we know that there's no H4O. So those mathematical constraints are also there. So I would tend to believe that there are no fermions beyond three generations, except right-handed sterile neutrinos of three generations. I think the right-handed neutrino probably showed up somewhere in your talk also. I don't recall.
Yeah, I think. Well, what I didn't talk about was where the way that the E6 embeds the E7. You get basically a copy of H3O and its complex conjugate under the kind of
Yes,
E6. So you get kind of
yes,
left and a right-handed sector basically.
yes, absolutely, absolutely.
But the Lorentz group, or the external spacetime, is only embedded in one of those H3Os, not the other.
Mhm.
So that gives you an asymmetry between the left and the right. And
Yeah. So in my picture, there is a second copy of a flipped 4D spacetime in the other E6. in the other copy of H3O, and that has 3 time coordinates and 1 space coordinate. The two have an intersection so that together it becomes a 6D space-time with 3 times and 3 space coordinates. What you call time, I would call proper time, and that T1, T2, T3, I mean, or X0 in your notation. I mean, I call that the time coordinate, which I agree with you, doesn't have the status of time that flows. That is, I very much like your picture of space-time evolving in an extrinsic time. The world does not evolve in time. No, the space-time manifold evolves in time. Yeah, it's not that spatial hypersurfaces you have a time evolution. The space-time 4D manifold itself is sort of flowing.
Yeah, I mean, it can be seen as like a river, I think, of like a block structure.
Yeah.
It has
There
that
we agree,
intrinsic flow inside it. Yeah.
Yes.
Yeah.
There we agree, yes.
Yeah.
Bernd,
did you have more questions?
Of course. Sorry.
We have 15 more minutes. Yeah.
Okay, then I will make it brief. You said at the beginning that you generalize proper time, but you say you're still in using Riemannian geometry despite using a different proper time. At least you said it's not Finsler geometry. Is it truly pure Riemannian geometry, or is it some kind of generalization? There's also something called Lyra geometry, which is also generalization going beyond quadratic forms. So,
right, I think a bit like I was saying with the lambda CDM model, I'm kind of trying to assume the simplest thing, at least to get a sort of a foothold in the theory. One possibility I have considered a little bit is kind of and I haven't looked at this recently, but whether Einstein-Cartan theory might play a role, so there could be the non-zero torsion related.
Okay, so torsion.
That's a possibility. That I mean, I don't have a definitive view on that, but that's one thing I've certainly
considered. But it would follow your philosophy, because Einstein-Cartan is the simplest generalization of general relativity.
But what about this E7 in the so-called Freudenthal geometry? I don't know anything about it, but I've read in Ramon's work that once you go over to this Freudenthal triple product and E7, you have a different geometry, which to my understanding is something new. It's like going from real numbers to complex numbers to quaternions and to octonions. You transit to different geometries. And at E7 level, something like, I don't know, have you come across Freudenthal geometries?
Not in the context of differential geometry. In the context of projective geometries, I have heard about it, but I would have to look this up. So far, not in the context of differential geometry, but that doesn't mean anything. It could be that there's something, a generalization of differential geometry based on Freudenthal triples, but at the moment I'm not aware of it. I'm only aware that
that could be significant. No, that could have.
Yeah, it could be significant. Yes.
Because it has an invariant triple product apart from an invariant quadratic form, and that is unique to things like H3O and E7. I have never been able to figure out what is the physical significance of this invariant triple product, which is only there when you're dealing with octonions and H3O. It is not there for the lower division algebras. So I think it could be related to what David said. This delta S cube, it's a kind of an invariant, right? Invariant under certain coordinate transformations like delta S squared.
Yeah,
right?
I mean, the delta S cubed is invariant under some large symmetry like E6 or SL3C, depending on the case. But then the physics symmetry is the broken symmetry, the product of the
Lorentz. No, but delta S cube is something like unification, yeah?
Oh, yeah, that is the unifying kind of form for...
So, delta S square and delta S cube are distinct invariants, right?
Yeah, I mean, ultimately in the physics, there's only one of them that sort of is the kind of highest sort of form, if you like, and that's either the E7 or the E8 case.
But what I remember from Ramon is that if you take H3O, it has an invariant quadratic form and an invariant cubic form, the triple product. The triple product now I see in your delta S cube. The delta S square, I don't know how to interpret the quadratic form, but it might have something to do with your upper 2 by 2 matrix that you have, sub matrix that you have shown.
Yeah, I think there are other related kind of algebraic structures relating to this kind of Jordan algebra and fundamental triple system, but I'm only mainly using these these cubic and quartic forms.
What is the physical significance of a cubic form being invariant?
Oh, just because I'm thinking of it as a kind of a generalization from basically this form, which is like a Lorentz invariance, basically.
No, I agree, but the Lorentz invariant basically telling us that in 4D spacetimes, because of constancy of speed of light, you have an invariant line element given the Lorentz invariant 4D line element.
Yeah, I suppose because I'm taking time as the fundamental thing, then this delta S is the basic thing. So whatever you do to these components, you shouldn't change this because this is the kind of the given element, if you like, this delta S.
Yeah,
So
I agree. I'm saying delta S cube being invariant should mean something in physics beyond special relativity.
well, I mean, I suppose, yeah, here, I mean, it's under this kind of broken symmetry that all of these components and the symmetry has a meaning. So there's this full symmetry before it's broken doesn't really have a meaning in the physics. It only has a meaning in the mathematics can start
I
with.
was thinking maybe if we use H3O for 3 fermion generations, then while there is some mixing between the 3 generations, there is some invariant in some geometric sense, and that is this delta S cube. It would be interesting to look at that, I think.
Yeah, I think my view, now I haven't kind of worked on this for a while, but I think when I was looking at these kind of possible E8 structures, I was looking at so building on E6 is a kind of H3O. I was looking more like a kind of H3O kind of almost embedded in another H3O. It's a little bit like the structure of magic squares, that they kind of use 2 copies of octonions, or maybe octonions and split octonions, and the way that they kind of work together. So I think one kind of element of H3O might come in relating to 3 generations, or certainly some kind of threefold octonion construction. But my original H3O for E6, that's kind of related to 1 generation in a way, or very closely related to 1 generation. And it needs some kind of embedding in some other kind of H3O type structure.
Okay, great. Thank you. Thank you. Thank you very much. Yeah, I think I think this is a very interesting perspective to relate H3O to a higher proper time, higher dimensional proper times. It is very interesting, I think.
Yeah, I think it starts out. I mean, originally I was thinking of extra spatial dimensions, and as a kind of naive experimentalist, I was thinking, why not add more and more extra spatial dimensions until you go to infinity? And like any other kind of infinity, that gets a bit dizzying when you think of more and more components. But the invariance of proper time ds is the same thing, so it kind of pings the kind of emphasis back on proper time. And once you're emphasizing proper time, you realize that delta S squared is only really needed for like spatial components.
Yeah.
As far as proper time is concerned, it's quite as happy to go to a cubic or quartic or any other kind of power.
Yes, I agree. Yeah, so are there more questions, please? Okay, otherwise, David, could you kindly stop sharing so that we have a gallery view of all of us who are here? Yeah, so I think not many are left right now, but some people are still there. So, so should we wind up, David? Is it okay?
Yes, great. Yeah, thank you very much. Yeah, thanks. It's been a
Yeah,
good
great. That was
discussion.
very interesting to listen to you. Really, I really mean that. I enjoyed this new perspective.
Yeah, sorry if I was a bit fast. I always put in more in the talk than when I'm
Yeah,
practicing the talk, it all makes sense to me. Obviously, when you're giving the talk, it's sort
I
of,
think the quantum gravity part, we need to think more, but the proper time part, I very much liked. It's when you write it as from 2 by 2 matrices to 3 by 3 matrices, that's a very obvious thing to do.
okay, that's good. I'm glad I got that part across. Yeah.
Yeah. So we meet 2 weeks from now. Antonino Marciano will talk on graviweak unification. And just a short note that that talk will be 2 hours earlier because Antonino is in China and 4 p.m. London time would be his midnight. So he will be very sleepy. So we started 2 hours earlier, 2 p.m. London time on 29th November. I'll send an email to that effect, but just to sort of put it in your system, the next talk is 2 hours earlier than usual. Yeah. Okay, great.
Yeah.
So should we log out now?
Okay, well, thanks everyone for tuning in. Thank you.
Thank you very much, David. Thank you, everybody. So I say good night to you now, and I will close this session.
Great.
Bye-bye.
Okay.